Hi, welcome back. In today's video, we're going to be having a look at operator decomposition, OD. This is going to be a kind of a continuation of, if you haven't watched the previous video on Centralized A star, which is the first foundational idea of joint space planning, right, where we're going to treat all of our agents together as some central controller. Well, please go watch that video. If you've just come from there, welcome to operator decomposition. I'm going to treat this video kind of like an appendum to the previous, and I'm going to relate it. So you see that I already have some text up as well, and we're going to work with the same example on the right, and we're going to then again still go back and talk about the branching factor and depth and size of the search tree that comes out of operator decomposition, and we're going to compare that directly against the one that came out of Centralized A star. So why am I doing this? Well, operator decomposition is another extremely intuitive version, very easy to understand, easy to implement MAPF algorithm that is using a centralized controller. So we are looking down over all of the agents, we have full view, and we're going to control them together using, again, the centralized controller. Okay, so we previously described Centralized A star as being a joint space planning approach where we treat each of these agents as essentially one large agent which has many degrees of freedom. Well, I'm going to erase this last line here. We're still trying to treat them all as one agent, but we are going to divide now each time step. Okay, so each previous thing that was just one individual set of time. Before, a time step would mean all agents moved at the same time. Operator decomposition is going to decompose time as individual movements, individual actions, individual operators of agents. So we divide each time step into n operators. Right, so for each agent n is the number of agents, we're actually breaking up and separating each of their operators, and we're going to treat that like a different state, that like a different level. So we're decomposing the problem, and you'll see that it's going to start being much longer, okay? So that's kind of weird. So we're going to get into why this actually might be an advantageous way to view the problem. It's just a reframing of the same ideas, but it actually has its own advantages. I'm not going to get to it in this video, but in the next video, there is something called independence detection, right? So we're going to actually be able to very easily, very intuitively, find which agents are actually ever going to interact. So imagine there was some far away agents, agent 3, all the way down here, that was never going to interact with the path of agent 1 and 2. Well, you would describe that as an independent group, an independent agent over here. So the idea of independence detection is really interesting, but what's really exciting is OD plus ID is actually a surprisingly performative algorithm. So the operator decomposition by itself is similar to Centralized A star. We're going to show it has the same size search tree, but when you pair it with independence detection, we can get really exciting results. So this is the difference. I want to then, of course, let's jump back over here, and similar to Centralized A star, let's draw up what the actual state space looks like that I'm discussing. So we're going to have the same idea. It's exactly the same as before. So your agent at C2, well, this still has 5 moves, but we're not looking at all possible ones at a time. Another way to view operator decomposition is that essentially your state now is not only the location of an agent, but it's almost like the location and its intended next move. So we'll show that in a second. So we have C2 and B3, just like we did before. So this is our first initial state. Now we're going to see that things deviate quickly. So we have our initial state, but we're going to see that the branching factor here is going to be substantially different to Centralized A star because only we're essentially, by decomposing it, only one agent chooses its actions first, and then in the next layer, the next agent will choose its actions. So we're going to get these things called intermediate states, right? So it's like there's now a difference in nodes. So in the search tree, they're kind of treated the same, which is interesting. But we know, right, that there'll be these intermediate nodes that don't actually correspond to a real full time step in the actual environment. So let's do this. So let's say that the yellow agent is going to be the one that takes its moves first. So we'll see that it can go up, right? C1. It can go right, D2. It can go down, C3. It can go left, C2. C2. And of course, it can wait still, which is C2. Just on the board. Now, that means that in this sense, the pink agent hasn't had a chance to move yet. So its location is always B3, and that doesn't change. Yeah, that's nice. Just on the board. All right, so let's then draw our squares. These are our states. These are intermediate states. Now, so all of these are what we call intermediate states. So obviously, right, this does not correspond yet to an actual full time step in the board because the pink agent still hasn't chosen. In the next layer, when pink now chooses its action, the next one will not be a dashed line. These will be states that are standard states, full time steps. So I'll draw the connections. So here we have only 5 states in the first layer. So we're going to start describing our branching factor in depth. Let's reason over how, we'll do that at the end. But the branching factor is going to be, remember I'm using the term B. B is going to essentially correspond to the number of actions available for each agent at a time. So in our 4 connected grid map, that's just a standard 5. N is going to be number of agents. And K is going to be time step of solution. Right, the actual time step in the real world problem, which as we said, one of the agents is going to have a cost of 4. One of them gets to go straight to their goal. The other one's going to have to wait 1 time step for the other agent. So one will have 4, one will have 5. Therefore, K would be 5 in this problem. It took 5 time steps for all agents to get to their goal. Now let's continue. So I'm going to draw out just one of the nodes because obviously this would be true for all of them. So when we go to draw this, we'll have that now, right, the C3 is locked this time. I'll only draw a few of them, I think. So maybe I'll erase this. There'll be a lot of dots in this instance. And so what we're doing is the pink agent gets to have its pick. So, you know, it can go right, of course. So this is C3. Then it would do B4, A3, B2, and B3 as the waiting move. If this is the third one, I've been doing it as right, then down, then left. So left here would be A3, whatever. So we have our states as you intuitively expect them. I've just drawn 2 states here. Now we know, of course, that we're seeing again, this is a conflict, of course. Both agents cannot exist at C3. So we'd go to generate this node, but it would never be generated. We immediately recognize that this is a conflict and it's pruned from the search space. Now we'll kind of come back and discuss how this actually changes the problem and what and very subtle advantages this approach actually has. But let's maybe start to describe this in terms of our search tree size. So this one is very easy to see. So in the first one, in the first layer, of course, start node, we have 1. Now we only have 5 states, right? There are only 5 things available. This is just our B, right? This is the number of actions each individual agent has available to it. And now we get to the next layer where for each of these 5 actions, you could do another 5 things. Well, this is going to be B squared. In the next one, then you have B squared times another B things, right? B cubed, ... Okay, so this is actually way more simple, right? The branching factor of the problem actually just remains at B, right? which is nice and easy. But what we can see is that the depth of the solution is going to increase, right? Instead of just getting to k time steps, that doesn't happen at layer k. Think about it, right? The number of intermediate states is going to kind of correspond to the amount of agents you have. So what's happening is instead of going down k times, you have to go down k times the number of agents you have. So the first true state, right, this would be like standard states again. It's confusing. I don't know why I'm drawing boxes around these. It's just to highlight it. This is not a state. Each of these individual boxes are states. So my bad. But yeah, so these are standard now. And this occurs at depth 2 because there were 2 agents, k times n. Now, to reason over the search tree size, well, this is actually extremely easy. ... It would be plus b squared, plus b cubed, so forth. It's just b to now just the depth of the solution, kn. Okay, so that is interesting. Let's what I would do here then to write out what the full size of this geometric series is, as I use the formula, and essentially what we arrive at is b to the kn plus 1 minus 1 over b minus 1. Okay, this is very, very similar. Now, similar to the Centralised A star video, here is where I do the hand-wavy math, because really we're just trying to describe this in a very general asymptotic sense, in big O notation, right? Talking about kind of like the computational complexity. Well, this is where the b minus 1 is it's a constant, right? Compared to the scale of these terms here and the number of nodes in the overall tree. Well, this is constant, minus 1 is obviously constant. So this very hand-wavy just goes to kn plus 1. So this is for operator decomposition. And what we had for Centralised A star was actually bn to the k plus 1, which is, this is equal to b to the kn plus n. Okay, so that is looking very slightly different. But they're essentially comparable, right? They're both essentially just b to the kn. It just means that the overall size of these trees are very, very similar, right? Because realistically, all you're doing is subbing out, instead of in Centralised A star, where we have very large branching factor but shallow depth, operator decomposition is reframing the way we view the problem, so that the branching factor is very small, right? The horizontal width of our tree is way smaller, but we do have to dive further down the tree to actually find the solution. Okay, so what are the subtle advantages of reframing this problem? So the difference is very subtle, and it comes in this idea that because the tree is so much deeper, it means we can actually do these we're doing this collision check more finely, right? You're doing the collision checks every time you're looking at just one agent's operators. And that means we can actually start to prune things very slightly earlier than we otherwise would, right? Instead of having to generate the full state and then we realize there are things to prune, well, it can subtly happen earlier. And it's not just about pruning. So in a similar sense, because we're treating each one of these intermediate states as a standard node, well, what it means is that overall, OD actually reduces the number of surplus nodes. Surplus nodes means nodes that you would have had to generate and store and maintain in this heap, but we were never actually going to need to expand at all on our way to the solution. So by the time we find the goal and terminate search, all the remaining nodes that are still generated but not yet expanded in the tree, these are what we call surplus nodes. So that's kind of related to the kind of like the memory use in the problem, as well as obviously how much like additional effort we kind of had to put in for these heap operations that didn't end up being useful to us. So operator decomposition very subtly actually reduces the surplus nodes as well, because we wouldn't have actually continued to generate these, right? Like it could just be that this state here was never interesting, and so we never had to look at it. We had just continued to expand things in promising directions. And so you kind of subtly save out in some of these operations and things you would otherwise need to do. And in the same sense, this happens when you're able to prune entire like subtrees of things a little earlier than you otherwise would. But they're kind of the same, right? Which is the interesting part of this. And so I think what you need to do then is to stick with me for the next video, where we introduce independence detection, pair that with operator decomposition, and all of a sudden you can start to see that just by a very subtle reframing of the problem, well, we can actually get pretty damn good performance for very, very similar ideas. So yeah, I think all of this really speaks just the idea that like the way we as humans frame and model the problem actually does matter in very subtle ways that aren't always immediately apparent. So please join me in that video, and thanks for watching.